Yeah, you can see the slides.
Yes, sir.
All right. So today we are going to see some number theory, some congruences, and as I said yesterday, we'll recall some things. We'll see some new things, hopefully, and in the end, we'll see some things related to binomial coefficients. So that's our overall plan for today. So let's get into it since we are already behind time in some sense. So first we'll have the introduction as usual. I'm told that you might have seen some of the things already, so just consider it as a revision. And the second part will be about congruences, which also some of you have not seen, some of you have seen. So do consider it a revision. Maybe some of the proofs that I give are a bit different than some of the proofs that you may have seen. So I think there will still be enough to learn either way. And in the end, as I said, there will be some special congruences regarding binomial coefficients and so on, and that will be useful later. Okay. All right. So introduction, and of course today we'll begin with some elementary number theory, and there are two important tools that we have at our disposal. One is unique prime factorization, which is that for every non-zero integer n, there exists a factorization into powers of primes, and there is a sign involved because we are considering all integers, positive or negative doesn't matter. So we denote it this way: negative 1 power epsilon of n times a product of primes. So epsilon of n is 0 or 1 depending upon whether n is positive or negative. The product is over all positive primes p, and of course an infinite product of that kind doesn't make any sense, but these exponents, which we denote as order of n for p, or whatever, or p of n, they are non-negative integers in general, and it is 0 for all but finitely many primes. So when it is 0 for most of the primes or infinitely many primes, then you're just multiplying by 1, right? And so the product does not have any problem. You only get like finitely many primes with a non-zero power in the exponent. And so all p of n is the non-negative integer a, such that p power a divides n, but p power a plus 1 does not divide n, the largest power of p that divides n. And this is fairly standard notation. You will see it in many other places. So this is how we write it, unique prime factorization, most generally, because otherwise we have to put p divides n in the bottom and so on. It's like sometimes this general form of writing helps quite a bit actually. Okay, so you probably have seen this before. This is one of the most fundamental results in mathematics. And the other tool that we have at our disposal is the division algorithm, where if you have two numbers, two integers, a and b, and say b is greater than 0, then there exists a quotient q and a remainder r, also integers, such that you can write a is equal to qb plus r, with the remainder strictly less than b, and it could be 0. So it's between 0 and b. But the most important fact that the division algorithm gives you is that the remainder size is strictly less than b. And moreover, q and r are unique. You can divide a by b in only one way in some sense. So my question to you, not an exercise, but just a question if you want to explore, is that how would you modify the division algorithm to include b less than 0? Typically have b greater than 0. Yeah, Sai has raised his hand, so please unmute yourself and ask your question.
Sir, it's not a question, it's more like answer to this question you just posed about b lesser than 0.
Yeah.
Because if you have a is negative and then you have q is positive, then you will have to have b is negative. So that will work. If you have Q is positive and A is negative, maybe.
Yeah. So what you are saying essentially is that any fraction A over B can be written with only one negative sign in the numerator. If there are two negative signs, you can just cancel them. Right.
Yes. So
Yeah.
if you want B to be negative and B to be lesser than 0, in that case, you need to make A or Q, one of them negative.
Correct. Yeah, that makes sense. But also, if you really want, you can also write a version of this statement with absolute value of R instead of just R. That's also possible.
Oh,
And
but
so the
then
absolute,
if you are dividing using negative integers, example, negative 10 divided by 5, you will get 2. Negative 11 divided by 5 is 2 remainder number 1.
negative
Yeah.
11 divided by 5 is,
If you have
sorry,
a negative number
negative
and you're
2 is
dividing
supposed.
it by a positive, if you divide a negative number by a positive number, your remainder is still positive. It's never negative.
Yeah. Of course. Yeah. Somebody else raised the hand. Siddharth did raise his hand.
I actually wanted to say the answer for the same question which Sai was talking about.
Okay.
Just remove the negative and make B greater than 0, solve, and then put the negative back in.
Yeah. It's basically what he said. Correct. Yes. It's a fairly simple question. I just want to, throw it out there in some sense. Yeah. It's not like a very difficult thing. Correct. All right. So let's go ahead. These are the two important tools that I just wanted to recall: unique prime factorization and division algorithm. And in many ways, I consider division algorithm to be much more fundamental than the unique prime factorization, actually. So just keep that in mind in some sense. All right. So we're now going to talk about greatest common divisor. And here the proof that I have chosen to give is a bit different than what you may have seen. Maybe you have seen the same proof, I don't know, but probably this is a bit different. So if you're given n integers, a1, a2 up to an, then we define I of a1, a2, an to be the set of all integers of the form a1 x1 plus a2 x2 plus up to an xn, with x1, x2, xn allowed to vary as integers. Okay. So you'll get, for particular values of x1, x2, xn, you will get some integer when you perform this operation on these given. You have a1, a2, an are fixed. Okay, those are something that is given to you. Like a1 and a2, you could have n is equal to 2, and a1 and a2 would be 2 and 3. And then this I of 2, 3 would be the set of all integers that can be written as 2x plus 3y, for example. Does that make sense to everybody? If you have 2, 3, and 4, then you will have 2x plus 3y plus 4z, for example. Yes, Siddharth.
Is this a definition of greatest common factor?
No, I'm coming to that. This is the beginning for that.
Okay, so
this is called the ideal generated by a1, a2, an, but I don't want to tell you all these things right now. But yeah, this is not the greatest common factor right now, but we'll come to that. Yeah. So yeah, currently this is just all the things that, you can have any a1, a2, an up to whatever, but for today's talk, we actually only need 2 integers. Like we don't consider 3 or 4 or 5. So, but I just wanted to give you the general definition, because why stop at 2? But today's talk, you have a and b, any 2 integers. Then you consider the set of all possible combinations of ax plus by, where x and y are integers. So you'll have a plus b, a plus 2b, a plus 3b, or you'll have 2a plus b, 2a plus 3b, whatever, a minus b, a minus 2b, b minus a, for instance, Okay, is that clear to everybody? Yeah. All right. So the key thing to notice is that the sum and difference of any 2 elements of this set are again in the same set, because you subtract a1 x1 plus a2 x2 from say a1 y1, a2 y2, you're going to take a1 times y1 minus x1 plus a2 times y2 minus x2, and that is still an integer combination of this form. Is that clear to everybody? Just
Yes, sir.
fairly
Can you repeat
straightforward.
once?
Swasti, sorry, could you repeat?
Can you repeat once?
Yeah, I'm saying that if you have any two elements of this form, say a1 x1 plus a2 x2 plus up to an xn, and then you have a1 y1 plus a2 y2 plus an yn, then if you subtract the second from the first, then you're going to get a1 times x1 minus y1 plus a2 times x2 minus y2 up to an times xn minus yn, right? That's just subtraction. But that is also an integer of this form, so it lies in the set.
Yes.
Yeah, is that okay?
Yeah.
Yeah. So sum and difference of two elements are again in this set, because sum you add, difference you subtract, but each time you will get an element of the same form. And also, if there is something in this set of this form, a1 x1 plus a2 x2 whatever, and there is some integer in R in Z, then if you just multiply this number a1 x1 plus a2 x2 by R, then again you can put the R inside, then you will have something like a1 times rx1 plus a2 times rx2 up to an times rxn, which is again a number of this form. Same thing, a1 times some integer plus a2 times some integer, and so on. Is that correct? Is that okay? Yeah. Yeah. So sum and difference and multiplying by anything in integer, any integer, you again get something in the same set. That is all. That's all. And as a special case, for a single integer a, if you have only one integer, I of a is just all multiples of a, like, right? I mean, that's the definition. You have only one thing. So you just multiply. You will have a and 2a and 3a, and on the other hand, you will have negative a, negative 2a, negative 3a, and so on. Okay, so far, everybody with me? Yeah. Good. And so now comes a key fact that's very surprising in some sense. If you have two, as I said, we are only going to look at like two integers of this form at most today. And so if you have a and b that are integers, then I of ab, this linear combination, the set of linear combinations of a and b is actually I of d for some integer d. Okay, you don't need, if you have like you don't need two generators in some sense. You have a different third generator for this set. Okay, so the statement is clear to everybody? Yeah. And I of d, for instance, remember that it is just multiples of d. So all that we are saying is that anything of the form ax plus by for is a multiple of one single common d. And so the proof is remarkably simple in some sense, but we'll see it very nicely. If say one of the two, a or b, is a 0, let's say a is equal to 0 without loss of generality, then I of ab is just, you will have 0 times x1 plus b times x2. So that 0 part just cancels away and you just have multiples of b. And so if a is equal to 0, then I of ab is just I of b. And if b is 0, then I of ab is just I of a. Everybody okay with that? And the statement is true. In that case, you can just take d to be either a or b, depending whichever circumstances you are in. And so now we can assume a and b both non-zero. And if a and b are both non-zero, then there will be positive elements in I of ab. Because if a is say positive, then of course a is in this set, so that you're done. B is positive, then again you're done. Otherwise, you just take negative a or negative b, for instance. Okay, so far? Yeah. And so if there are positive elements in I of ab, then of course you can choose the smallest positive element in this set. Okay, so this is quite an important step in some sense, this is a kind of an induction process. But you have to for choosing for choosing the smallest positive element in I of AB, I need to know that there are positive elements in the first place. So make sure that you never make this mistake of logic. Like you might say, just choose smallest positive element somewhere, and then there are no positive elements. How can you ever choose one? Okay. So the last step was just to make sure that there are positive elements here. And this sort of a rigor is really necessary in mathematics in various places. And you may not see that in your school level mathematics that much, but when you see these kinds of things, you have to be very careful. So then, yeah, so let D be the smallest positive element in I of AB. Then by definition, D is inside this set. Oh, sorry. D is inside I of AB. So we saw that if D is inside I of AB and R is any integer, then RD will lie again in I of AB. We saw that in the second paragraph on this slide. Right. And which means that all multiples of D are going to lie in I of AB. And so I of D is all multiples of D. So I of D lies in I of AB. Okay, so far? Anybody have any questions?
Sir, I have a question, Raghav.
Yeah.
Sir, I did not understand how I of D will be a subset of I of AB.
Yeah. So yeah, I of D is just all multiples of D. You're okay with that?
Yes, sir.
Yeah. So in the second paragraph, the line beginning with also, you see that also if I belongs to I of A1, A2, An and R is any integer,
Yes,
then I can multiply I with R, and then it will again lie in the same set, I of A.
yes.
And
Yes.
so since I of D are all multiples of D, and any multiple of D has to lie again in the same set by that also line. I of
Yes,
D
sir.
as a set completely lies inside I of A.
Yes, sir. Thank you, sir.
Yeah. Okay.
Yes, sir.
Yeah, so if I want to show, I chose the notation D for a reason, that this D must be the D that I want. Otherwise, it doesn't make any sense. So we have to show the reverse inclusion, that anything in I of AB, I have to show that it is a multiple of D. Yeah, okay, so far. If I want to show that two sets are equal and one of them is contained in the other, then I can prove that both are equal by showing the reverse inclusion. If you have not seen this kind of a technique, then just pause a bit. I'll just let you think about it a bit, and if you have seen it, But it's a very interesting technique again. Especially these are infinite sets, so you cannot count their size or anything. For example, otherwise, if I have two finite sets and I want to show that both of them are same, then you can show that one of them is inside the other, and then you show that the sizes are the same. So of course, then the subset has to be the whole set. But these are infinite sets, so I cannot talk about any sizes or anything. So we have to show this reverse inclusion. All right. So now let C be any element of I of AB. Okay. And then I want to show that C is a multiple of D. Okay. C is an integer multiple of D. But then this choice of smallest positive integer D was made for a reason. Of course, C is an integer, D is an integer, so I can use the division algorithm. Yeah, and write C is equal to QD plus R, with R strictly less than D. But then you see, both C and D are in I of AB, and on the previous slide we saw that sums and differences of any two elements in I of AB will also lie in the set. Is that okay? You recall that from the last slide? Sorry, this second paragraph again. Yeah. And so C minus QD is a difference of two elements in I of AB. But that is R. Correct? So R should also be in I of AB. But D is the smallest positive element. Sorry, there is a typo. I wrote smallest instead of smallest, but that's fine. But D is chosen to be the smallest positive element, and R is also positive, possibly 0. But if R is non-zero, then it is positive, and it is smaller than D. And it is contained in I of AB. So this is the contradiction. So R cannot be positive. R has to be equal to 0. Does that make sense?
Sir, could you please repeat? I did not understand.
Sorry, could you speak louder, Jayaditya?
Yes, sir. Sir, could you please repeat this part? I did not quite get it.
Sorry, I can't still hear you. Like if anybody, maybe Sundar can hear you. Yeah.
Yeah, he's asking you to repeat this part. He didn't get it.
Ah,
The last
yeah,
part.
yeah. Just repeat, right?
Yeah,
the
just
question.
repeat. Yeah, just
Yeah. Okay. Yeah, I'm saying. Do you agree that C can be written as QD plus R? Right? That's just
Yes.
the definition. Yeah. So, so C and D, C is an I of AB, and D is known to be in I of AB.
Yes,
So,
sir.
so from the previous paragraph, for example, the difference of two elements in I of AB is again in I of AB. So, for instance, C minus D would be in I of AB. But then C minus D will also be in I of AB.
Right. So C minus QD will also be in IFA.
Yeah, correct. Yeah, that's okay.
Yeah.
Yeah, but C minus QD is R. So R is
Right.
in I of AB. So far, so good?
Yeah.
Yeah. But then R is smaller than D. So if R is positive, then it contradicts the choice of D that I made in the first place. D was supposed to be the smallest positive integer in I of AB. And now I am exhibiting you something, an R, which is smaller than D, also in I of AB. So if it is positive, then that's so. Why did I choose D in the first place? I should have chosen R in the first place, but that's not how the choice went, which means that R has to be 0. If R is positive, then this is a contradiction.
Got it. Thank you, sir.
Yeah. Okay. So far,
Yes, sir.
great. So R is 0. But if R is 0, then C is a multiple of D. Yeah, C is QD. And C was any element of I of AB to begin with, the first line of this slide. So any element of I of AB is a multiple of D, which means that it belongs to I of D. And so on the previous slide, I had shown you that I of D is inside I of AB. And now I'm showing you that anything in I of AB is contained in I of D. So this is the reverse inclusion.
Thank you,
Got it?
sir.
Yeah.
Yes.
Yeah. And so I'm done. I of AB is the same as I of D as the set. So as I've mentioned, this division algorithm, I consider it to be a better tool than unique prime factorization in many ways. And R for this property that R has to be strictly less than B or D in this case. That is very important because otherwise I could not argue this way. Great. And so now we'll see why this is related to a greatest common divisor. So of course everybody knows this definition, but I'm slightly changing it from the usual definition in the sense that I'm not requiring as of now that the greatest common divisor be positive or anything. So let A and B belong to C, and integer D is called the greatest common divisor of A and B if D is a divisor of both A and B, and if every other common divisor of A and B divides D. And note that if C is another greatest common divisor, then C and D divide each other, and so C must be plus or minus D. So the greatest common divisor for me is chosen up to a sign. But once you put the greatest part, it's determined up to a sign, like it could be plus or negative. Later we'll choose the positive number as we usually do. And so this is a small lemma that that we did not do all of this I of AB business for no reason. If I of AB is I of D, then D is the greatest common divisor of A and B. Okay. Sai has raised his hand. So go on.
Sir, I did not understand. It is the greatest common divisor. So if C is a negative, then how will it be the greatest?
Yeah,
Because-
yeah. So the reason that I'm saying it as the greatest is that I'm not putting any size relation here.
Oh, okay.
I'm not saying that the size of D has to be the greatest.
Okay, I got it.
Yeah, that's why. Yeah, it's a minor distinction really, but I prefer it this way. The reason is that this what do you say? This formulation of I of D, for instance, you're taking all multiples of D, but then D could just be minus D, and you will get the same set. So
Oh.
long as we are talking about the sets here, then we don't have to make the choice of D. You see what I mean?
Yes, sir, I got it.
Yeah. So then D is. So I'm talking about a greatest common divisor rather than the greatest common divisor right now. When I say the, like it means it's fixing some unique element. And so the is typically reserved for positive. I'll come to that in a minute. But let's see the proof of this lemma first. Yeah. And so So the contention is that the set of ax plus by for all x and y, if it is generated by this, if they're all multiples of some d, then that d is the greatest common divisor of a and b. Well, the proof is 2 lines. If a is in I of d and b is in I of d, so but these are multiples of d, so d is a common divisor of a and b, right? By definition. And suppose that c is a common divisor, then c divides every number of the form ax plus by because it divides a and it divides b. So it divides each of the terms inside the sum. Right? C divides a, so c divides ax. C divides b, so c divides by. C divides ax plus by. But then d is a number of the form ax plus by because the sets are the same. And so in particular, C has to divide D. Okay, so far? Yeah. And so this satisfies the definition of any common divisor. C divides, has to divide this D, which is also a common divisor of A and B. So D is the greatest common divisor. Okay. And so, yeah, as I said, it is customary to take the greatest common divisor of A and B to mean to be the positive such integer. And we denote this integer as A comma B. And so the notation A comma B that you have seen probably many times, it actually comes from the notation for I of A comma B. You have this I of A comma B with 2 brackets. And in fact, in like number theory books, people won't even write the I part. They will just write A comma B as the set and also A comma B as the greatest common divisor. And the reason is that both of them are equal in some sense. So I did not want to like confuse you because you're young. So I put like an extra I there just to. Yeah. And so it's very useful in the sense that, the greatest common divisor can be written as a linear combination of A and B. Ax plus by is D. And I don't know if last week or like last year, did you see Euclid's algorithm by any chance? Have you seen it?
Yes.
Yeah. So this is a non-deterministic form of Euclid's algorithm. Here I'm telling you that D exists as some Ax plus By, but I'm not telling you how to compute X and Y. And that is actually possible from the same proof actually, but since you have already seen, I thought you would have seen it, so I don't want to give it again. Yeah. And so here, this is a non-deterministic way of saying that the GCD can be written as Ax plus By in some way. Yeah. So note that we do not give a method of computing this greatest common divisor, but only have proven its existence. And this can be computed by Euclid's algorithm, as you would have seen. Yeah. Okay. And so now we come to a statement that is frequently called Euclid's lemma, which you must have seen again if you have seen all these things before. Suppose that A divides BC and that the GCD of A and B is 1. Then A has to divide the other term. A has to divide C. And the proof is that since GCD of A and B is 1, there exist integers R and S such that RA plus SB is equal to 1. You can compute them via Euclid's algorithm, for instance. And so you multiply both sides by C. And so therefore you get RAC plus SBC is equal to C. And A divides RAC. There's an A there. And A divides BC by hypothesis that's given to you. So if A divides BC, then A divides SBC. And so A divides RAC and A divides SBC, so it divides the sum. And so A has to divide C. Clear so far? Yes, okay. Again, you might have seen these things, but just good to have a revision. And in particular, a direct corollary is that if P is a prime and say P divides BC, then P divides B or P divides C. And the proof is clear, like if P doesn't divide B, for instance, then GCD of P and B is 1 because P is a prime. And so P has to divide C. So I'm not writing down the proof of that. And another corollary is that this is very important in some sense. Suppose that P is a prime and A comma B belongs to Z, belongs to the integers. Then the order of P dividing AB, the largest exponent of P dividing AB, is simply given by the addition of the two largest exponents for each individual A and B. This is not true if P is not a prime. Like 6 can divide something. 6 does not divide 2 and 6 does not divide 3. But 6 divides their product. So if A and B are 2 and 3, then order of say 6 dividing 6 is 1 on the left hand side. But on the right hand side, you will get both to be zeros. So 1 is not equal to 0. So P has to be a prime for this. It's very important. So these two are very important corollaries of these, and this proposition or its first corollary is frequently known as Euclid's lemma. This is Euclid proved it first while proving the unique prime factorization theorem. And again, as I said, these things could not be proven without the division algorithm. And unique prime factorization comes after this. So in some sense, division algorithm is more fundamental than the prime factorization. Okay, so this finishes the introduction part of today, like recalling what you've already seen in some sense, and hopefully given you something new to think about with all these I of AB and I of ABC. Like, I'm not giving you any exercises on those parts, but if you really want, you can say, why stop at 2 numbers? You can say I of ABC, and you can find that this is also, they also have a GCD, right? And 3 numbers will also have a GCD, 4 numbers will also have a GCD. And so you can see that even there, all the analogs of statements that we have made, they will remain true. Okay, so now we'll go to congruences. And the definition, first definition is innocuous enough, simple enough. You have 3 integers A, B, and M inside C. M is known to be the modulus by classical language. We say that A is congruent to B modulo M simply if M divides the difference B minus A or A minus B. And this relation is written as A congruent to B modulo M. It's with 3 lines to suggest that it's not an equality, but rather it is this state. In many ways, you can treat it as an equality also, but in many ways you cannot also. So We'll see some of that later. Okay, so this is the definition which many of you may have seen before. And these are some simple properties that A is congruent to A modulo M, of course, because M divides 0, which is A minus A. So that's fine. And you might like laugh at me saying, why are you saying such a simple thing? But sometimes these things get quite difficult to check also. So if A is congruent to B modulo M, then B congruent to A modulo M. So the first statement means that M divides B minus A. The second will mean M divides A minus B. Of course, if one happens, then the other has to happen. And the third statement is that if A is congruent to B mod M and B is congruent to C mod M, then of course A is congruent to C mod M. Because you can have B minus A plus C minus B is C minus A. And fourth is again simple, is A is congruent to C mod M and B is congruent to D mod M. Then you can add the two sides and you can take products as well. You cannot divide. Make sure you understand that. Taking addition or product is okay. Subtraction is also okay because subtraction is a different way of adding things. But you cannot divide. In general, sometimes you can, but that's a very different thing. All right, so this is another definition that that won't play much of a part today, but maybe later I can use it sometime. So I'll just give it. So if A is an integer, let A bar denote the set of integers congruent to A modulo M. But then if you think about it a bit, this is just the set of integers of the form A plus Km for K belongs to C. It's an arithmetic progression beginning at A and with a difference M. Because you subtract any of integers of this form, you will get a multiple of M. And so all of them are congruent to each other modulo M. That's what it means. And we call such a set A bar a congruence class modulo M. And if A1 bar, A2 bar up to AM bar are a complete set of congruence classes modulo M, there will be M many of them. Like 0, 1, 2. You must have seen all of this. 0, 1, 2 up to M minus 1, for instance, is a complete set of congruence classes modulo M. And then we call A1, A2, AN is as a complete set of residues modulo M. Okay, so far? Okay. So what we want to do is we said that this is like an equality. So we want to solve like linear equations, for instance. Like you have solved linear equations maybe in school or somewhere before, I think. And so here I want to now solve the simplest congruence, which is like AX is congruent to B modulo M. Or in other words, AX minus B is congruent to 0, which is like AX minus B is equal to 0, right? It's like a linear equation. But the first difference to note is that unlike in the real numbers case, this congruence can have many solutions, not just one. Okay. If you want to say X minus B is equal to 0 in real numbers, you say X is B divided by A. There's nothing else. But here, this kind of a thing is not true. And so why don't we take like a couple of minutes to find all solutions to 6x congruent to 3 modulo 15. Siddharth has raised his hand. So go on.
Actually, there does exist a very simple way to solve it, but it's an infinite family of solutions. I'll tell the smallest one soon after I solve it.
Yeah, sure. Yeah, so why don't we solve this question right now? 6x is congruent to 3 mod 15. Find all such x. Yeah, Raghav, yes.
Sir, x will be congruent to 3 mod 15.
Yeah, that is certainly one solution. Are there any others?
Actually, the general thing is 3x is congruent to 1 mod 5. That's the general.
3x or 2x?
3x. I mean
3x.
2x. Sorry, 2x.
Yeah.
Yeah, 2x is congruent to 1 mod 5 is general. In this case, you can divide, but you have to divide the modulus as
Yeah,
well.
so why we can do that is a question that we'll come to it later. But right now, just do this problem.
So there is one classic solution. X equals 3 is the easiest that you
Yeah.
can find. X
But what are
equals
the
3
others?
works. X equals 8 also works. If you stick in
like
x equals
equals-
Or
8.
x is equal to n
13.
such that 3n plus 5. Yeah, that will work.
Yeah, x equals 3 mod
Yeah.
5. Every solution in that form works.
Just
Yeah.
x equal to 30, x congruent to 13 mod 15 will also work.
Yeah,
so
5
3,
plus
8,
Sir,
and
three.
13.
x should be congruent to 3 modulo 5.
Yeah,
3
x is
modulo 5.
Yeah,
yeah.
all the solutions are in the form 3 modulo 5. Every
I just
solution.
wrote it in a linear fashion, 5n plus 3.
Correct. Yeah, so it can be checked that, for instance, 3, 8, and 13, if you only restrict to residue systems, then 3, 8, and 13 are solutions to this.
Oh, you're only risking to residue systems. Then 3, 8, and 13. That's all.
Yeah. I mean, talking about infinite solutions is okay, but like we are ultimately modulo 15. So why do we want to consider all of them inside? So yeah, I mean, you can, as everybody has said, like 18 is also a solution and so on, right? And 23 and so on. So, yeah, good. So this kind of a working already tells us a general way. Like the reason that I gave you this example is to generalize this in a nice way.
I found a generalization.
Yeah, great. We'll also come to that. I'm slower than you, Siddharth, so
It involves a lot of algebra, but you can get the general solution.
Yeah.
Not that much.
Yeah, it's not a big deal. We'll just see it. So yeah, how do we find all solutions to such a congruence? First, we can safely assume that A is not 0. Because if A is 0, then 0 is B mod M. So you see it. Solution directly. And let D greater than 0 be the GCD of A and M. And as some of you have already seen, like some of you already talked about cancelling the 3 out of the equation, for instance. And so that is what we want to do, essentially. And so we'll introduce some notation is that divide A by D and call it A prime, and divide M by D also and call it M prime. And now you see that if I've taken the GCD out, then the GCD of A prime and M prime is 1. There are no other factors to be divided. Yeah. So why is this? Okay.
There is one thing weird about division in modulus. Sometimes you have to divide everything, A, B, and M. Sometimes only A and B. Don't divide M.
Yeah, that's we'll see why that is actually true in some sense. And so let's see the proposition. The congruence AX congruent to B mod M has solutions if and only if D divides B. That's the first thing. If D does not divide B, then there are no solutions. And if D divides B, then there are exactly D solutions. And if X naught is a first solution that you find, say by trial and error or whatever, then the other solutions are given systematically just by adding multiples of M prime, which is M over D, M divided by D. So in the previous case, if you notice, you found the solution 3 first, and then M prime would be 15 divided by 3 in that case, so 5. So then you will have the solutions 3 plus 5, 3 plus 5, 3 plus 10, 3 plus 15, and so on, for instance. Okay, so there are exactly D solutions for the residue system. Obviously, if you consider only over integers, then there are like infinitely many. Because once you have one solution, you can just add multiples of M to it. But 3, 8, and 13 are not congruent to each other modulo 15. So in some sense, they are distinct. And so this is generalizing what you worked by hand in the previous example. And so, for instance, if x, so we have to show the first part that it has solutions if and only if D divides B. So for say x naught is a solution, then ax naught minus b is my naught for some integer y naught by definition. Right? Ax0 minus b is congruent to 0 mod m, so this is my0. And then you just take the terms, you just swap the terms b and my0 on the other side. And now the GCD D divides both terms on the left hand side. D divides ax0 and D divides my0. So D has to divide B. So if there is a solution, then D has to divide B. Okay, so far? And the
So
other
D
part,
is the GCD of A and M, right?
yeah, D is the GCD of A and M. Yeah. So now let us suppose D divides B. Now we know that by the previous discussion that there exist integers P and Q such that AP minus MQ is D. Right? The GCD can be written as a linear combination of A and M. And now I multiply by B over D on both sides. And this is an integer because D divides B. That is our hypothesis now. And so if I multiply by this B over D, which is denoted by C, then you will see that A times PC minus M times QC is B. And so we have solved the linear equation. Yeah, okay so far? Yeah, so the first line is proven. If there exists a solution, then D divides B. And suppose we start with D divides B, then I have provided you with a solution. So this is an if and only if condition. And the second claim I'm not going to prove. This is an exercise. Yeah, like once we start with this, it's fairly simple. You have already done it for the previous question. So now you just have to generalize 6 to A and 3 to B and M to 15, so on. So show the remaining claim about this number of solutions and their form. And so, yeah, just by way of an explanation, this for the congruence 6x congruent to 3 mod 15, we need to solve this equation 6x minus 15y is equal to 3. And then as Siddharth said earlier, you can divide by 3 everywhere to solve 2x minus 5y is equal to 1. And x is equal to 3 and y is equal to 1 is a solution to this. So x naught is 3. The first solution that you find is 3. And then m prime is 5 in this case. 15 divided by 3, for example. And so 3 plus 5 and 3 plus 10, 8 and 13 are also solutions. This is the theorem applied, the proposition applied to this particular case. Okay, so far? Good. There are two important corollaries. If A and M are relatively prime, then Ax congruent to B mod M has one and only one solution. So in this case, this does behave like an equality, like a linear equation, is what I'm saying. Earlier, you got like 3 solutions for a linear equation, which is not what happens usually, right? But if GCD of A and M is 1, then in fact, this behaves like a linear equation. This is the content of this corollary. And the proof is simple. In this case, D is 1, so D divides B for any B. 1 divides B. And there are D is equal to 1 solutions. Okay? Yeah, and sorry, there is a typo here. A should be not congruent to 0 mod P. Sorry. Must have blimped. Okay. If P is a prime and A is not congruent to 0 mod P, make sure that you don't write A congruent to 0 mod P. If you're thinking there's a typo. But then Ax congruent to B mod P has one and only one solution. The same thing. Right? M is P in this case, and P does not divide A, which means that it's relatively prime too. Okay. So now let's see Chinese remainder theorem, which you might have seen already. And so first we need a couple of lemmas. If A1, A2 up to AL are all relatively prime to M, then so is their product. And again, by unique prime factorization, it is simple, like direct. But I rather give a proof that does not involve unique prime factorization, just because I like I like to do this. So the proof is fairly simple. If the product was not relatively prime to M, there will be some prime P that divides them both. But then P has to divide one of the AIs at least, because if P divides a product, we have seen this, P divides a product, then it has to divide one term. And then it contradicts that the GCD of each individual AI with M is 1. Okay. So fairly simple. Again, I mean, you can prove it yourself, but I just thought. So if things are relatively prime to M, then the product is also relatively prime. Now we go to the other end. Say everything, there are T numbers given to you, A1, A2, AT, and they all divide N. But such that they are relatively prime to each other. Then their product divides N still. And if the relative prime condition is not true, then this obviously fails. 4 and 8 divide 32, divide 8. But their product does not divide 8. Yeah. So this is an exercise. Just to make sure you know what we are working with in some sense. It's the same circle of ideas that we are talking about. Do unique prime factorization, do whatever you want, but just prove it. And then the statement of the Chinese remainder theorem is that suppose that M is like composite or whatever, it's made out of, it's written as a product of M1, M2 up to MT, such that the GCD of individual ones is 1 if they are distinct. And let B1 up to BT be integers, and we have a system of congruences, not just one congruence, but a system of congruences, X congruent to B1 mod M1, X congruent to B2 mod M2, and so on. Then the claim is this system always has solutions. You'll always find one X which satisfy all of them together. And furthermore, any two solutions, they differ by a multiple of M, which means that modulo M, it's unique. And so the proof is again not too difficult. Let Ni be M over Mi. Then by lemma 1, the GCD of Mi and Ni is 1. Okay, it's a product, if I is 1, then it's a product of say M2 up to MT. And that GCD is still 1. And so thus there are integers Ri and Si such that Ri Mi plus Si Ni is 1. And let Ei be the Si Ni part of this. And then by construction, Ei is congruent to 1 modulo Mi, where it satisfies this equation. Okay, so far. And Ei is 0 mod Mj for all the other ones, because Ei contains this Ni, and Ni contains all the other mod M2, M3, M4, whatever. Okay, but then set X0 to be just sum of Bi Ei for each I. We're constructing, like for each I, we are constructing this individual solution and just adding them together in some sense. And then again, there is a typo, sorry, X0 is Bi Ei, but Ei is 1 modulo Mi. So X0 is Bi modulo Mi. And thus this is the solution. Yeah, so this is, so till now we have been seeing like propositions and lemmas because they're simple. This is a theorem, so it takes some time to see in some sense. Have you seen this already? Like, have you studied Chinese remainder theorem already? No. You have seen the Chinese remainder theorem, but not the proof. Is that? That's okay. That's what I'm saying. Yeah, yeah. So this is the proof. So again, like it will take some time for you to assimilate what's happening, but Sorry for the typo here, but other than that, the proof should be okay once you like think about it a bit. So make sure like when you get a recording or something, just see about it, see what's happening. You know, you have to do it by your hands, maybe just to, you have to write things down and then you'll get it. Okay, so far? All right. And so an exercise is to prove the second part of the theorem, that any two solutions differ by a multiple of n. And for this, you need lemma 2. So again, it's a simple verification, but and we'll explore these relatively prime integers modulo m in more detail. And the number of all relatively prime integers modulo m that are between 0 and m is denoted as phi of m, which you must have seen sometime. And we have the concept of a reduced residue system modulo m, similarly, where now you have phi of m many integers, all of them pairwise incongruent, and the GCD of all of them with m is 1. You take all the relatively prime integers less than m, for example, it satisfies. Okay. And the first lemma is that if a is another integer whose GCD with m is 1, then if you multiply all of the reduced residue system members by a, then you again get a reduced residue system modulo m. So it's like a translation, you know. And so there are two conditions to be checked. I'll check the second one first. I check that for any I, the GCD of AAI with m is 1. But that's just true by the lemma 1 that we saw. If you have two things that are relatively prime to m, then the product is also relatively prime to m. Okay. And so we just need to show that they're pairwise incongruent, which means that if two things are equal or congruent modulo m, then the indices has to be the same. They cannot be distinct. And then you just write down what it means. AAI is congruent to AAJ modulo m. Then m divides a times AI minus AJ. But since the GCD of A and m is 1, which means that m has to divide the other thing by the lemma that we saw some time ago. And AI is congruent to AJ mod m. But to begin with, this was a reduced residue system before you multiplied by A. So if AI is congruent to AJ mod m, that means I has to be equal to J. Makes sense so far? Yeah. Okay. Yeah. So you have a reduced residue system. You take another relatively prime thing, multiply, you still get one. That's the statement. Why do we want this? You might have seen this statement again already. Euler's theorem. Might have also seen the proof. This way. No? Okay. Yeah. So this previous thing about reduced residue system will help us see the proof, basically. So if the GCD of A and m is 1, then A power phi of m is congruent to 1 mod m. And the proof is that since both of these are reduced residue systems modulo m, when you take the product, you know, individual members might be different. But when you take the product, all of them together, both of them have to give you the same thing. They're multiplying the same things in possibly different order. Yeah, makes sense? And so the first line is the first equation is this product. So you can take the a power phi of m out. It's a common factor. Not a common factor, but you can take it out. And you see that a power phi of m times this product is congruent to this product again. And so you want to cancel the product. You know, like if you have AB congruent to AB equals to B, then you want to cancel this term. And you can do that in this case. You cannot always cancel. But in this case, the GCD of M and this product P that I've denoted at the bottom, this is equal to 1. So if M divides this a to the phi of M minus 1 times this product, then M has to divide the other term, which was to be shown. Make sense?
Sir, could you please repeat?
Yeah, so you're okay about the second equation, is that fine?
No, sir. Actually, I lost you from the therefore statement.
You lost me at the,
Sir, from here, sir. After this, I did not understand anything.
okay. Yeah, so each of the term on the left hand side has an A, right?
Yes,
There
sir.
are P of M, many of them.
Yes, sir.
So that will give you an A to the phi of M.
Yes, sir.
That's okay. So I'm just like
Yes.
taking it aside. And
Okay.
then you have the product of AIs that remains. And
All
on
right.
the right hand side, I'm not doing anything. That's the same product.
Got it, sir.
Yeah. Okay.
Thank you,
So
sir.
now, so do you have like all the proof, or do you want me to explain the other things as well?
No, sir, I got it.
Okay.
Thank you, sir.
Yeah. No problem. Yeah. Yeah. So yeah, M divides A to the phi of M minus 1. Okay. Good so far. And so yeah, just a warning is that you have this kind of a cancellation property, which we used in the last lines, where if AB is congruent to AC mod M, it is tempting to say B is congruent to C mod M, but this doesn't always hold true. If the GCD of A and M is 1, it will hold true. But be careful with that. Okay. Yes, Siddharth.
In the other cases where it doesn't hold true, you have to divide by the modulus as well.
The GCD, yeah, you have to divide the modulus by the GCD. Correct.
As well for it to work. But a division is possible in some way or the other.
Yeah, but then you change the modulus, then you have different problems in some cases. It's
Yeah,
not
but
the same
sometimes
problem.
you need to, just like we showed this mess right here.
Yeah. But changing the modulus is a more
Here we
more
needed
fundamental
to
operation
change
in
the
some.
here we needed to change the modulus.
Yeah. So make
Here-
sure you have this in mind always. It's just like a silly mistake to make in some sense.
Yeah, and this is the solution. I've just written it down.
Okay, so let's go ahead. And so an immediate corollary is that if P is a prime and P does not divide A, then A to the P minus 1 is congruent to 1 mod P.
Fermat's little theorem.
Yeah. Actually, Euler proved it. Interesting.
Yeah,
Fermat
by
did not
his
give any
own
proof.
theorem.
Yeah. And then, yeah. So this is an important definition. So I just want to give you in the last few minutes that we have. Let A and M be such that the GCD is 1. Then we say that A has order E modulo M if E is the smallest positive integer such that A to the E is congruent to 1 mod M. So we know that there exists at least one positive integer such that A to the E is congruent to 1 mod M. We saw that is P of M. And so now I'm saying again, this is the issue that came from earlier. If you want to choose the smallest positive integer out of something, you have to show that there are positive integers there. And so choose the smallest one and call it the order. And this is a nice exercise. Show that if A has order E modulo M, then E divides phi of M. Okay. And the last part, in the last 5 minutes or so, we will focus on binomial coefficients. Back. Yeah. Some special congruences. And so please allow me like a couple of minutes extra because we started late. So, possibly we'll
Okay,
go
sir.
a bit beyond time, like just a couple of minutes. We have only like 3 slides, right? Not much. So the congruences we'll see now are quite useful in mathematics. In fact, very useful in the research that I do as well in some sense. So you can see how fundamental they are. So the first proposition is that if P is a prime and K is an index for the binomial coefficient, which is strictly less than P and not 0, then the binomial coefficient P choose K is divisible by P. And the proof is using the multiplicative definition, as one might guess. You just write down the definition and then cross multiply to clear out denominators. As you have p factorial is the product of these three terms. Okay, so far, yeah, it's just definition. And p divides the left hand side clearly, but p cannot divide p minus k factorial, or p cannot divide k factorial, because k is strictly smaller than p. So this is a product of integers that are strictly smaller than p. Then how are they going to get a prime factor of p? Make sense? And so p divides the left hand side, so and it does not divide the first two things on the right hand side, so it has to divide the third. That's all there is to it. Yeah. And so this leads to a fascinating lemma, which I really like. So one of my favorite lemmas when I started learning these things. If L is greater than 1, in fact, equal to 1 is also fine. But anyway, doesn't matter. And A congruent to B mod P power L, prove that if you take P power on both sides, then in fact, the modulus you can do better, not just P power L, but P power L plus 1. Okay. So in some sense, raising to power P makes congruences better. Like you have extra powers of P that come into picture. You see what I mean? Like A to the P is congruent to B power P mod P power L. That's trivial. You can just multiply. But I'm saying here that actually you can do better. You have more information. Okay. So on the next page, we'll see the proof of this lemma. And so write A is equal to B plus C times P power L for some C. That's the definition. A is congruent to B modulo P power L. So A has to be of this form. And now raise both sides to the pth power. And so you will get the binomial theorem. You will write down all terms. So I'm not writing down all terms, but you will see that except the first two terms in the binomial expansion that I have written down, all the other terms will have at least a P power L plus 2 in it. And if you just write it down, okay, because you will have P to the 2L and P so on, right? And so, if the other terms have P power L plus 2 in it, then obviously they will be divisible by P power L plus 1. It's a larger power. And so I have to only worry about these two parts. And so by the previous lemma, there is a P in P choose 1. And there is already a P power L. And so you get a P power L plus 1. So T is divisible by P power L plus 2, which is divisible by P power L plus 1. And this second term is also divisible by P power L plus 1. Which means that 8 power P is congruent to B power P modulo P power L plus 1 here. Sorry, there is a typo. The statement that we want, basically. Okay. Sorry for the typos, Today there are a couple of them. So yeah, this is P power L plus 1 is what I want to say here in the last line. Make sure that you make that change. And so we have proven the lemma. And so corollary is that if L is greater than or equal to 2 and P is not equal to 2, then I can take our number of the form 1 plus AP and raise it to P power L minus 2 part. They take P power. So on. And this is congruent to 1 plus A P power L minus 1 modulo P power L. And so this kind of a stuff is later useful in the Bernoulli numbers issue. So I just want you to have this statement right now. Okay. But I'm not going to prove it. You have to prove it. And use induction on L. And use this past couple of lemmas and propositions and so on. Okay. The same set of ideas. You have binomial coefficients. You will have some, you're raising to P power L minus 2, like. So you'll have some binomial coefficients and just see that the congruence matches in some sense. Okay, so use induction, prove the exercise. And congruences of binomial coefficients are useful in a variety of places, and we'll encounter them again when we study Bernoulli numbers, like this kind of statements. Okay, and yeah, and that's it for today. Sorry for the lateness and sorry for going over time for a bit. I was a bit too rushed today this morning. So. Okay, so far, yeah. So you have a few exercises here, and I've also